Are there any questions? Any questions about the online homework? Sailor, right?
Yes, teacher.
What was your question? Have you already finished the first chapter? It hasn't opened up because I haven't put it online yet.
Okay.
Any other questions? If there are no questions, I will come up with some questions of my own. Dug through a trash can, and I don't think I can see how many calories. So 5.
Yeah, 5 total.
Oh, right there. It does. So let's use that, and I'll ask you a question. How many joules and 5 calories? There's the question. Sugar-free electrolyte. Guess you add that to your bottled water and makes it more exciting. All right, what did we learn yesterday? How about 4.184 joules per calorie? Any difference between the top calorie and the bottom calorie?
Yes.
Yeah, we also learned that 1 nutritional calorie
is 1,000 normal calories.
So y'all like conversions and units. You realize units are your friends, right? Good. So I got to pay attention to my uppercase. So I got uppercase calorie in the top. I want lowercase calorie up top. So there is my conversion factor to get calories to go away. Now that I'm into calories, I can look up here at this unit equation. Put 1 calorie in the bottom, 4.184 joules up top. Everything's going to do what it should. And now I can go 5 times 1,000 times 4.184 joules. There's my number of joules. Joules are kind of small. Quite often we work in kilojoules. All right, how do you feel about that one? Pretty good? So we studied about a thermochemical equation. What is a thermochemical equation? All right, while you're thinking about that, I'm going to write one down. I'm going to take some aluminum, take some oxygen, make some aluminum oxide. I guess I should worry about the phases. Sometimes it makes a difference in thermochemistry. So now I have a thermochemical equation. So now if I ask you, what's a thermochemical equation, you can tell me, right? So, well, it's a chemical equation, but we have a heat involved. So now I get to ask you some questions here. Is heat a reactant or is heat a product? So we learned something about the signs of enthalpy yesterday. It is a product. Very good. It is a product, and we know that because of our enthalpy is negative value. Negative sign is less than 0. All right, normally we just spell the word endothermic or exothermic. I broke it up here a little bit. Is the reaction endothermic or exothermic?
Isn't it exothermic?
Absolutely. It is exothermic. Let me ask another question. Use this very scientific word here called things. A good scientific verb, get. Do things get hot or cold? Things probably means the surroundings.
I'd say it's hot.
Yeah, it gets hot. So I've had students tell me they go out camping and they get a big bonfire. And I've heard of people throwing a magnesium rim on a bonfire. What's that sound like?
Loud.
Well, if you can get the thing lit. All right. So maybe some more questions up here to see how you're doing with Chem 1. See what you forgot, what you remember, maybe what you covered. How would you classify this reaction? Single replacement, neutralization. Synthesis is good. It is a combination. I got 2 elements on each side. So what's the oxidation state of aluminum here? Since it's in its elemental form. It's 0. And what's the oxidation state of oxygen there? It's 0. Any element in its elemental form, 0. Alright, so over here we have aluminum in the +3 state, oxygen in the -2 state. And that's why I almost messed up my subscript. That's why we have those subscripts. So yeah, it's a synthesis or combination. We could also call it a redox reaction. Alright, enough of that. This will be something new. We'll get to it in the slides, but it'll give me something to talk about. How much heat is evolved? We get to say the word evolved now because we know it's an exothermic reaction. Heat is given off. That is why the surroundings get hot, whether that's flask, or now we're going to qualify it. 25 grams of oxygen react. So in a slide coming up, I'll probably say enthalpy is an extensive property. There should be a vocab word from Chem 1. What does extensive properties mean? Let me give you some intensive ones. Density and color. Doesn't matter how much you have. You can look at a little piece of snow and tell me it's white. You can look at a glacier and tell me it's white. All right, enthalpy. Amounts matter. All right, I'm going to just rewrite this equation since I did such a horrible job up above because I forgot my subscript. And we need this thermochemical equation to answer this question here. So I'm going to look up here at the given and say that's probably where I need to start. 25 grams of O2. What do I need to do with my 25 grams of O2? Everything in chemistry proceeds through the what? That creature with claws and sharp teeth. What? 1 mole of O2 should be pretty close to 32.0 grams of O2. Look up there and see roughly 16 for oxygen. I got 2 oxygens. Some of the older books, they just don't write what your new book does. And that's a mole there. And notice moles of what?
Isn't it going to be oxygen?
Well, yeah, for whatever's in the balanced equation here. For 2 moles of aluminum that get used up. For 3 moles of oxygen that gets used up. For 1 mole of aluminum oxide that forms. So per mole,
So it's per mole of aluminum oxide, correct?
Well, watch this. I need to get rid of my 1 mole of oxygen, right? How am I going to do it? I'm going to look up there and I'm going to say for every 3 moles of O2, how much heat gets released? 3,351 kilojoules. So enthalpy is an extensive property. When you have the thermochemical equation, which is a balanced chemical equation, and the heat associated with that per mole means however it's written here. And so we can ask questions about aluminum, oxygen, or our product of aluminum oxide. And then we can look at our good friends, the units. And I converted grams oxygen to moles oxygen. Moles oxygen goes away when I look at the coefficients in the balanced chemical equation, which says for every 3 moles of oxygen consumed, we're going to get this much heat. So all my units did what they were supposed to do. Now I can pull out my calculator and go 25 divided by 32 multiplied by 3351 divided by 3. So I'm going to just go to 3 digits. 873 kilojoules of heat is released. All right, any questions about this problem? All right, I was supposed to ask at the beginning of class, what is the first law of thermodynamics? Right, old book used to call internal energy E. It makes a lot of sense, but you know how it is, got to be like everybody else. Physicists and engineers call internal energy U. So we want to be consistent here. The total energy, U, of the system is called internal energy. So internal energy here, we have some beginning state, and so here we can lose energy to the surroundings, and we'll end up at a lower state. Here, if we go to a higher state of internal energy, we'll be up higher. See, this needs energy, so this would be like an endothermic reaction. This thing here loses energy.
So that's an ectothermic then.
Right. So like that first problem, negative 3,351 kilojoules. Aluminum oxide is at a lower energy state than a given mass of aluminum and oxygen. Reducing agent and oxidizing agent. Once they react, they're at a lower energy state, and all that energy is given up. So it's nice to talk about these things because we want to figure out these signs. And so down here it says energy loss to the surroundings. Internal energy of the system decreases. Our delta U is negative. For right now we can say that's probably related to delta H. And here delta U is positive if our final state of the system is at a higher energy than the initial. So I typically ask students, like on a quiz, state the first law of thermodynamics in both a sentence and an equation. And you're all warmed up for the sentence because everybody told me energy is conserved, it cannot be created nor destroyed. What is the equation? Delta U, any change in internal energy, is equal to the sum of heat and work. Delta U equals Q plus W. So here's the equation form. So we think of the system as being the chemicals themselves. So when work is positive, we say it's being performed on the system and it can raise it up to a higher energy state. If the system does work on the surroundings, work is going to be negative because that's going to want to lower the internal energy. And we got the same thing going on for heat. If heat is positive, we're putting heat into the system and the change could be positive. Let's just say work is 0, then of course it's positive. So exothermic reaction, we just looked at one, gave off lots of heat. And if you just took some aluminum metal and put it in oxygen-rich environment and got it to react, might be hard to harvest any work. So a lot of heat goes off to the surroundings. Any questions on this slide? So the system is the chemicals themselves, as described in the thermochemical equation. Surroundings, it's the rest of the universe. So these sign conventions, using that equation. If we have a positive Q value, that means the system gains heat. If it's negative, it means the system loses heat. Same thing for work. If it's positive, it means work is done on the system, raises it to a higher level perhaps. When W is negative, that means work is done by the system. All right, so delta U equals Q plus W. There's a balance there. If we have a positive change in delta U, that means there was a net gain of energy by the system. If delta U is negative, that means we have a net loss of energy by the system. So we got a little bit warmed up with this on Monday, and then with our warm-up problem, endothermic means that it absorbs heat from the surroundings. And the reaction container typically could feel cold. Thermic means heat is transferred to the surroundings. Things typically get hot. So this is a rehash of those sign conventions. So what's a good example of an endothermic reaction? Reaction container feels cold. Think about Monday. Oh man, that was 2 days ago. Yeah, the ice. Ice going to liquid water. It's endothermic. Drawing. I drew a squiggly line going into the ice cube. Ice cube was the system. All right, we're going to find out that enthalpy is a state function. What does that mean? State functions depends only on the initial and final state of the system, because that's something we can kind of measure. Sometimes we don't know the exact internal energy of a system, but we can measure change under stated conditions. So that kind of is a mnemonic. Stated conditions, probably a state function. However, we do know that the internal energy of a system is independent of the path by which the system achieves that state. So here we got 50 grams of liquid water at 25 degrees Celsius, and it could have came from 50 grams that was at 100 degrees Celsius, or we could have had 50 grams of ice and melted it and heated it up. So we know something about the state here. Now we have 50 grams, it's liquid, and it's at 25 degrees Celsius. All right, pretend that's a delta U. So here's a good picture of these concepts. If you take a battery and have just a wire coil, the electricity runs through there and the wire heats up. Think about your toaster oven, and all the energy gets lost as heat. Don't try this at home, it won't work. 1.5 volts trying to run a fan. But anyway, you get the idea. Here the blade turns, exerts a force through disc, performs work, imparts some kinetic energy to the air, gets it moving. And here we both have the same energy loss of the battery. So the battery is losing internal energy, delta E or delta U, as the book likes to call it, is changing, it's going down. And if you touch your fan motor, you feel it gets warm, or run a vacuum, or most electrical appliances, especially if you're overworking it, you can burn up the motor. How does the motor burn up? A lot of the electrical energy gets converted to heat. But here we see work and heat being both done. Here just heat being done. Q and W are not state functions. Other ways chemical systems can do work. Here's a piston in an enclosed cylinder. Like the other day, we saw a gas in there. So when this thing moves up and down, there's pressure from the atmosphere poking down. If this thing moves up, it's going to do work on the surroundings. For this thing to move up, the system is going to have to lose energy. And maybe if you played around with pistons, you might imagine this is at a higher energy state than this, because you have this compressed gas. This thing's going to want to maybe pop up if you release the force. And here this thing's expanded, it has less energy. Usually in an open container, the only work done is by a gas pushing on the surroundings, or by the surroundings pushing on the gas. So here's a good example of a fun chemical reaction. We got zinc metal reacting with acid. We're going to do something real similar today in lab, and we get hydrogen gas. So this is a single replacement reaction you'll recognize. This thing probably heats up, but as that gas forms, this thing expands, pushes up the cylinder. So here's an equation for work. There's at least one homework problem like this one, and I always like to put one on the quiz. So here's a good example. Determine the work done in joules when a sample of gas expands from 45.2 liters to 89.1 liters at constant temperature against a constant pressure of 1.25 atmospheres and against a vacuum. All right, I think I'm just going to work part A. So there might be some things we need to write down. I'm going to write down that 1 liter per atmosphere is the same thing as 101.3 joules. And let me see if I can be tricky. So we have work.
It's frozen.
That's all right. You'll have to use your imagination. So there's my equation, and I know the pressure on that first, on part A, says 1.25 atmospheres. And my change in volume, I'm going to go final minus initial, so I'm going to go 89.1 minus 45.2. So here's where we're at. So here's my change in volume. Here's my pressure. So I thought the book's explanation was a little weak on here, but they gave you a unit equation in there. There it is, and we get to use that to work our way through this. So work, got to have an energy unit, and I see an energy unit of joule here. So I'm going to go negative 101.3. Let me start all over. Work equals negative 101.3 joules per atmosphere liter, down in the bottom. Liter atmosphere. All right, then now I get them right in the pressure, and now our delta V 43.9 liters. And if everything went right, atmospheres goes away, liters goes away. What unit am I left with? I'm left with joules. Alright, I think I solved this on the PowerPoint. I kind of slammed it together in a different order. Went over, sorry to do that. I'll see you again